Okay, good morning. Friday. Spirit Friday. I'm going to keep my cap on today. Okay, so today we're going to go through the notes or the slides pretty quickly so there's time for questions. Okay, you'll have some questions on the homework, no doubt, but hopefully this morning I'll answer a few of those. We're going to be talking about the transition equation today and a little bit about the transition moment integrals that you guys have been doing in the lab. Okay, so that's the main point for today, is talking about the intensity of the spectrum. That's the transition dipole moment integrals. And then also the spacing in the spectral lines. So that comes from the transition equation. So in terms of spectroscopy, light has to interact with the system in some way. And light is an oscillating electric field. So it's best, really, it's almost a requirement for that particle or something in that species to be charged. Like you can have a neutral molecule, but within that neutral molecule you have nuclei and you have electrons. And so light's going to interact with those charged species even inside a neutral molecule. And so we need also an unequal population of energy levels. Because if the particle absorbs that photon of light and goes to a higher transition, but you have a molecule that's in the higher transition and it gets hit with light and is stimulated to emit, you're going to see the same amount of light on the other side. And so you won't notice that transitions have occurred if the populations are exactly equal. This is part of the problem in NMR, and it's why we need higher and higher field magnets so that we can increase the signal. Because the energy levels are so close together, there's really no difference at room temperature between the population of those nuclear spins in a small magnetic field. You put it in a large magnetic field, it splits those levels, and then the Boltzmann distribution gives you an unequal population of those energy levels. So that's why the more and more sensitive NMR spectrometers have huge magnetic fields, because they need to get that unequal population of energy levels. We also need a significant probability for the transition. So what is the piece? We have the Boltzmann piece, the transition moment integral, and the Gaussian line shape. Which one of those talks about probability for the transition? It's the interactive part of it.
The one with I.
I, yeah. So what does that I stand for? Always remember integral.
Integral.
Yeah, so the transition moment integral or the transition dipole moment integral is the probability piece. Okay. So why do I keep using these two terms, transition moment integral or transition dipole moment integral? Well, because we could be calculating the scattering. We're not doing that yet, but we will in the future. The scattering would just be the polarizability, which would be like a Raman or Rayleigh scattering experiment. And so that would just be called a transition moment. Whereas if you're doing absorption or emission, that light's interacting with the charged electron and that light's acting like a dipole. So a single photon experiment, that calculation would be the transition dipole moment because light's acting like a dipole. So I'll use those terms interchangeably, transition dipole moment integral or transition moment integral. And so then we also need interaction with an electric or magnetic field. So in our particle in a box, if we've solved for the energy levels, we have them plotted here. We have the first four energy levels. If you'll notice on the screen, we have the quantum numbers. The quantum numbers start with 1 at the lowest state and go all the way up. Here we have the first four. Notice that they're not equally spaced. Remember, it's depending upon n squared. And then we have these transitions. Arrows here going up are absorptions. See that? And then the arrows going down are emissions. And I've put some little pictures of charged particles on there. So let's say a Boltzmann distribution shows us that there's 3 charged particles in the ground state, 2 charged particles in the first excited state, and then 1 charged particle up in n equals 3. So we've got an unequal population, so spectroscopy is possible. We have charged particles, so it can interact with light. But what are the probabilities? So if we go to our lab work and we do those transition moment integrals, we could calculate the transition moment for this. This is a 1 to 2 transition. This is a 2 to 3. So you see the arrows, they're connecting those levels. And that's how we would label those different transitions. 1 to 2, 2 to 3. Over here, we have an emission, which would be a 4 to to 3 transition. It's going from level 4 down to level 3. Everybody follow the nomenclature? We also could skip levels. So here we have a jump. Okay, it's going from 1 all the way to 3. So this is a 1 to 3 transition. And then we could skip 3 levels and go from 1 to 4. Okay, so that's really all I could fit on this diagram. It's pretty busy. And so we need these 3 things. We've already seen this in earlier slides. I just have it in this PowerPoint to make it complete. You need intensity, which is related to the Gaussian line shape. You need the Boltzmann distribution, which tells you the unequal population piece, that thermal population. And then the probability is the transition dipole moment squared. Now, how do we get X to represent light? Think of it as a light coming in on this one axis. We have a particle in a box, and if light's coming in on that axis, you just line that electric field of light along that axis. And so it has a positive end and a negative end, just like an electric field. So we can use the x-axis and then multiply that by our wave function. And that's as if that electric field is interacting with the wave function. And that's how we calculate that transition moment integral. And so here are the results. So if you were to check my work, I have a 7 angstrom box, I have an electron mass, and these are the wave functions for particle in a box, and these are the intensities, the transition moment integrals. So this is as if I went and talked to people who had the 1 to 2 transition. They would have gotten 1298. The 2 to 3 transition was 1514. The 3 to 4 was 1576. So all of those are pretty strong probabilities. Notice they're not normalized. They're not 0 to 1. So they haven't been normalized to give us a true probability. But relative probabilities, those are in the 1500s. And notice that some of these are 0. So the 1 to 3 and the 2 to 4 have a 0 probability. Those integrals, when you looked at them, they had integer multiples of pi and all of the signs, and things canceled out to where those integrals were 0. Notice also what's interesting is if you swap the wave functions, so 2 and 3, and you swap that with 3 and 2, they're the same number, and that's kind of handy. So this is telling us that stimulated absorption and stimulated emission have the same probability. That word stimulate is important. I'm stimulating it with light. So a photon comes in and hits the particle and it could be absorbed. Stimulated emission is the same way, only a photon comes in, hits the excited atom or molecule, and causes it to drop down, and 2 photons come out. And that's how a laser works. So if you have a population in the upper state that's more populated than the ground state, and a photon comes in, you stimulate emission. Now you have 2 photons. They hit 2 other molecules and stimulate emission. Now you have 4 photons. And so it's light amplification by the SE, stimulated emission of radiation. So stimulated emission and absorption have the same probability. So if you have really strong absorption peak, you might be able to get a laser out of that substance.
Is there a pattern and trend where if, like, say, it looks like if both of them are even or both of them are odd, does it have a more tendency to be 0?
Yes, we're going to look at those patterns. And if you see here, I have evens. I have an even here, and an odd, and an even. The x-axis is odd. And so we can look at the symmetries of the wave functions, which are given by those even-odd designations on the energy levels. And we can look at the symmetry of the x-axis, and we can jump all the way to the end. We don't have to do the integrals. So all that work you did this week, we can do on a Post-it note. So how much paper did you use doing those transition moment integrals? Right? We can at least do the zeros right here. We can fit it all on a Post-it note. Okay. And so that's what's coming next when we get into symmetry. Okay. And what's also interesting is skipping levels is okay, but it's less probable. So if we had a delta n equals 3, it's still probable, but it's only 8 compared to 1500, right? So it's less probable than just going to adjacent levels. Delta n equals 1.
So 10.
Yeah.
So how is a 2 to 4 transition less probable than a 1 to 4?
this is just the overlaps of those wave functions, okay? And so, and 2 to 4 is 0 probability because it's only changing by 2 levels. And so you need to change by an odd number of levels, it appears. So we're looking at this and we're saying, every time we just jump 1 level, it's non-zero. If we jump 3 levels, it's non-zero. But if we just jump 2 levels, then it's 0. We can't do that. We can't make a jump with light to 2 levels.
Is that because like 2 pi, sine 2 pi 0?
No, this just is it's the odd even nature of the functions. Yeah. And so this is our conclusions for selection rules. And so this is a new term for you. It's called selection rules. Those are the non-zero probabilities. So they're the rules related to the quantum number changes. So selection rule tells you what quantum number changes give you non-zero probabilities. I'll go ahead and write that on the board just because I see some confused faces. And so this is the selection rule definition in a lot of words. So it tells you what quantum number changes yield non-zero TDM integrals. And I could also just say selection rule tells you what transitions are allowed. Okay. Expecting an important call, but I can't take it right now. Okay, so I'm going to move the camera over to that so that you can get that in the back. Okay. Can y'all see that? All right. So selection rule tells you what quantum number changes yield non-zero TDM integrals. And a non-zero transition dipole moment integral is an allowed transition. Important point. Got it? Okay. Okay, so let's go. And so in that particular result here, we have sort of deduced the selection rules to be delta n equals 1 or 3. It could be plus or minus 1 or plus or minus 3 because it's also allowed to go down in emission. We don't know about 5, 7, and 9, but in your lab you might have been assigned a delta n equals 5 or whatever. So we could poll everybody and we could make up a table with all of the allowed transitions and all of the forbidden transitions. If it comes out to be 0, we call it a forbidden transition. And so let's now talk about the transition equation. That was one of the homework problems. Here is the answer to one of the problems. It was for all transitions of delta n equals plus 1. And so if we have that delta n is plus 1 as a selection rule, where are those peaks in the spectrum? The transition equation addresses the x-axis in the spectrum. It tells us the location of those peaks because it gives us an equation that tells us the energy differences in those energy levels, and that's what's going to show up as spectral lines. Okay? So the transition equation tells us the spacing in those spectral lines. And so what we do for the transition equation is it's the difference in energy levels, and so we're going from n to n plus 1. And so we have the energy equation with respect to n here, and then we have the energy equation with respect to n plus 1 right here. So everywhere there's an n, we put in an n plus 1. And it's that simple. We take the difference. So we're taking all of the n plus 1 energy levels and we're subtracting all of the n levels. And you see that the algebra works out pretty nicely. So we can pull all those constants out front, and then we have a simple polynomial to evaluate, n plus 1 squared minus n squared. And so we get down here, it's nice that the squared dependence goes away because we have a plus n squared and a minus n squared. And so we're left with this equation. Now, it's nice in spectroscopy to have everything pulled out front so you just have the quantum number by itself, or as close to by itself as possible. So this 2n that's inside the parentheses, I'm going to go ahead and pull that out, and I'm going to have to divide the 1 by 2 in order to do that. And so this would be the format for the transition equation that I would like to see. Okay, they're both correct at the bottom, but this one is my favorite. Okay, because it just has n by itself here, and it's got some constant here that's related to the system. Okay, I mean, maybe, why don't I just call that p? Okay, some constant p. And then I've got this coefficient in front of it. So that tells me as my energy levels go from 1 to 2, and then 2 to 3, and 3 to 4, and 4 to 5, notice I'm changing n from 1, 2, 3, 4, 5. My spacing in those spectral lines is going to go up by 2 times this constant p. Now, why is that useful? Well, if I have those peaks in my spectrum and I assign them, I can then take differences of those peaks and I could pull information out. Let's say I knew my box length was 7 angstroms, but I had no idea what kind of particle I had in there. I could use that constant to find the mass of that system. Or if I knew it was an electron and I didn't know how big my box was, I'm getting a spectrum of this electron. It's confined to a space, but how big is that space? I could take those separation of those spectral lines and I could solve for the length of that space. So this is what we do in spectroscopy and physical chemistry. We'll take a spectrum, we'll have a model, and we'll use that model to learn something about the system. We've kind of done it from the bottom up here. We've said it's an electron, we've said it's confined to a 7 angstrom space, but most of the time we don't know exactly how big the system is. So we would take that model and apply it and solve for the size of the system. This is how we solve for bond lengths. And so y'all will do this when we get to carbon monoxide. You will take the spectrum and you will take you could take many differences of those lines, or you could do a linear regression and see how those lines depend upon quantum number. And the bond length would be buried inside that constant. Just like the length of the system is buried inside this constant. Yes.
So do you want us to make it to where it's 1n regardless, like even if you end up with like a really nasty fraction?
Yeah, it's like 3/2 or something, that's okay. Yeah. And so let's do another one. Let's do delta n equals 3. Y'all did 4 in the homework, so let's do 3. So if we want to look at all transitions that jump from 1 to 3, or by 3 levels, so 1 to 4, or 2 to 5, or 3 to 6, so everything is jumping by 3 levels, then this would be that transition equation. And so again, we just put n plus 3 anywhere there's an n and take the difference. So pull the polynomial out and pull the fractions, pull the constant out. Again, the n squareds cancel, and you have 6 plus 9. So I want to get that n by itself, so I pull that 6 out front. I don't leave it in the denominator and cancel the 8 or anything and make it like 3/4. I go ahead and leave that constant alone. That h squared over 8ml squared would be my constant p, and now I have a spacing of 6p between my levels for these, what we call overtones. So these are overtones, and we'll talk about that in a second. We'll label all the different peaks in the spectrum. But that way I still have that same constant p, but in an overtone series it's spaced by 6p, and in the fundamental or the delta n equals 1 series, the hot bands, we just have a spacing of 2p. This will be very familiar when we get to the rotational spectrum of carbon monoxide, because the spacing is 2b. b is the constant in that case. It's called the rotational constant. And buried inside there is the mass of the particle, or the reduced mass of the molecule, and the bond length. So let's put all this on a spectrum now. So here's the spectrum, stick spectrum of a particle in a box, And I've plotted it versus transition energy. In the past, the stick spectrum and the Gaussian convolved spectrum was in terms of wavelength, and we have a version of that here. But let's stick to the energy equation for now, because you can see if we plot it by energy, the peaks are equally spaced, and so that spacing would be for these blue bands. This spacing right here. Let me just find one here. So this spacing right there would be 2 times that constant p that I talked about. And then when we jump levels or skip levels, those are multiples of this fundamental frequency, and so we call those overtones. Just like an overtone in a guitar string, you play the fundamental, but if you were to look at an oscilloscope, you'd see 2 and 4 and 6, or 2 and 4 and 8 times that frequency. Those would be overtones or higher order resonances. And so they kind of got the name applied to them, these ones that jump multiple levels and go from 1 to 4 or 2 to 5. Those are called overtones. And so the spacing between the overtones that we just determined from the transition equation was 6p. But notice how in a whole spectrum, we have that constant p in the spacing between the spectral lines. And we could learn something about our molecular system by doing, if we had this kind of spectrum, we could take averages of all those differences and get not just our mass, but with statistics, plus or minus some uncertainty, or the distance or length L, plus or minus some uncertainty, because we have multiple measurements of the same constant. So this is the blue bands correspond to that transition equation that we just did, and so the green bands correspond to the other one. And so what does the transition equation tell us? It tells us about the x-axis in the spectrum, and it tells us about the spacing in the spectral lines. It's just, I'm really trying to emphasize that. Does everybody understand why we want to do the transition equation? All right. Now, if we plotted this by wavelength, then it's not equally spaced because energy and wavelength are inversely proportional. Okay. The nice thing about plotting things by wavelength is that fundamental transition, that 1 to 2 transition, the very lowest energy difference, is going to be the longest wavelength, and it kind of separates it from the pack. And so if we wanted to know what that fundamental transition is, it's probably best to take your experiment versus wavelength, because as you can see, the fundamental is separated from all the hot bands. Now, can you explain to me why the hot bands are called hot bands? No? I heard something back. Yeah, they start at an excited state. For the first hot band, you're going from level 2 to 3. And the next one's from 3 to 4 and 4 to 5. Those only happen if you have excitation, thermal excitation. So if you cool things down cold enough, everything collapses down to the ground state, and the only spectral signature you have is the fundamental. Because everything's in ground state. It's in n equals 1. And the only transition you're going to see is 1 to 2. You will see a probability of a overtone. You could go from 1 to 4. But that's not a fundamental transition, and it's a pretty weak one. Remember, it was a probability of 8 versus 1,500. So you might be able to see the first overtone, and you might be able to see the fundamental at cold temperatures, but that's all you're going to see. And the spectrum would be very, very simple. All we would see in very cold temperatures is this one here and this one right here. That would be our first overtone. So our spectrum would collapse down to just 2 peaks. And you might have a second overtone, which is going from 1 plus 5, so 1 to 6. But 1 to 4 was 8 relative to 1,500. And so 1 to 6 is going to be, in the decimal places. So we're probably not going to see that peak. I think the next figure, even though it's more busy, will really help you understand what's going on. Here, all those transitions are labeled with their quantum numbers. So now, hopefully, you can see what's going on with the spectrum. Right? So look what's going on. All of these here, this is the fundamental, and it's going from 1 to 2. And notice all of the hot bands start at some number higher than 1. So they have to have thermal excitation to exist. So that's why they're called hot bands. And then we have the overtones. The first overtone here is 1 to 4. So it could exist at cold temperatures. It could happen. Okay. But all the others start at higher levels, and they're just not as probable. And these are the relative intensities that I plotted. So if your blue peaks are that tall, your green peaks are that tall. Okay, so very hard to see. Notice the second overtone here still starts at 1, but it goes from 1 to 6. And so then you'd have to do the transition equation to figure out what this spacing was. Okay. But it would be some constant times p. So it would be some number times p. And this is what we call a spectral assignment. So if you were given a spectrum and I said, assign that spectrum, you would go in and you would pick all the peaks. You would find their frequencies, and then you would assign quantum numbers to that. So when we say assign a spectrum, or we're going to do a spectral assignment, we're going to take every transition that we see, and we're going to put quantum number transitions on them. And we're going to do that for the carbon monoxide spectrum. We can do that for the vibrational spectrum of chlorobenzene and benzene, and look at the symmetries of those things. We're going to do that for the iodine molecule. So we're going to assign at least 3 spectra in our time here, where we actually put the quantum numbers on all those peaks. So we actually know what's happening down at the quantum level for those spectra. Any questions about this? Any questions about the spectral assignment?
So for this one,
Yes.
this one would be the fundamental, would be the 1 to 2.
Mm-hmm. Yeah, so the fundamental transition is always that starting at the ground state and going to the very next one. Okay, and that's always the highest probability transition. So the fundamental should be your tallest peak.
And why isn't it?
Good question. Yeah, thermally it's going to probably be your highest peak, but you can have a little higher probability for the 2 to 3, 3 to 4, but then the Boltzmann drops off. So you can kind of see it goes up and then it drops off fast. The going up is from the transition moment integrals, and so sometimes they can go up. And we saw earlier went from 1200 to 1500, and at 1500 a little bit more. But that third one, let's just go back and look, just to see. Yeah, no, this thing is. We need to get another one. Okay, yeah. So the third one was still higher. Okay. But when we get to the spectrum, it was lower because the Boltzmann distribution started taking over. Okay, so the Boltzmann population of level 3 was so low that it took the intensity back down a little bit. We're going to definitely see that in the carbon monoxide spectrum. There, the peaks go up because of the degeneracy of the rotational levels. So it goes up strongly and then it comes off again. And the coming down is the Boltzmann distribution. The going up is the probability of the transition. And then plotting this same spectral assignment versus wavelength, it's pretty simple to assign this spectrum. You're probably going to see the 1 to 2 transition and the 2 to 3, but then all the others are going to be buried underneath one big peak. Now you could still solve for the same constants in this way with wavelength, but it's not going to be constantly spaced, right? But you could find if you had the location of that 1 to 2 peak, you could solve for M or L. So let's take a Kahoot and kind of reinforce the main points.
The 1 to 2 almost went a little lower than the 2 to 3 peak.
Yeah, it was a little bit. Yeah, I was trying to follow what you're asking.
And then it goes down.
Yes. And that's a function of temperature. So if I lowered the temperature, then those others would drop off very quickly. Okay, the game code is 555655.
So close.
What happened?
So close to all 5.
That's right. Is that everybody? Anybody waiting? Okay, so we have 5 people who think Fridays are optional. Oh, sorry. Talking bad about you. Anyone? Bueller? Okay. Oh, it got in just in time. Okay. Absorption and emission have the same probability, same transition moment integral result. True or false? Yay! I'd like to see that. Okay. The transition equation is related to which axis of the spectrum? The vertical axis or the horizontal axis? One more. Yay, horizontal axis. Good job. The transition dipole moment integral affects which axis of the spectrum? Vertical or horizontal? Oh, a little bit more of a split there. It's calculating the probability of absorption, so it's telling you the intensities. So the transition dipole moment integral is really important for the height of your peaks, and that's the vertical axis of a spectrum.
I thought it was the spacing.
Yeah. Okay. The transition equation tells us about the spacing of the energy levels or the spectral lines. Think about it. Don't screw up. A little bit more even split there. It's the spectral line. So that transition equation tells us about the spacing in the spectral lines. Remember I was saying the spacing was 2p or 6p, and so that came from the transition equation. So it's a difference of differences, right? Each individual spectral line is the difference in energy levels, and the transition equation tells us where those lines are. So the differences in the spectral lines is what the transition equation is giving us. We're using the energy level spacing to come up with the transition equation, but once you have it, it's telling us about the spacing in the spectral lines. Okay. So that's the energy equation tells us about the spacing of blank. Hopefully I swapped the correct answer because it was a copy and paste. Yes, so energy levels come from the energy equation, right? They tell us where those locations are, and you can get the spacing of those energy levels from the energy equation. Yay! All right. Okay, we've got a few minutes to field questions from the homework, or any other kinds of questions you might have. Life, the universe, and everything.
Is the answer A on the exam?
Probably one of them. Yes, in the back.
Okay, it was your work, but after the year term, the optional questions.
Yes.
This is where it was asking, convert E equals MC squared and, sorry, I don't have it right.
Yeah, take E equals MC squared and
Yeah.
equals h nu.
New to derive the Dipole
Yeah, yeah.
wavelength, and it said don't overthink it, but it's like I can't get it.
Okay, yeah, so let's do it. And the only trick there is that the speed of light then becomes a velocity that's less than the speed of light. Okay? So we have E equals mc squared. Oh. And E equals h nu. Okay? And what do we have? What's new? Okay, right. So we have all of these three relationships, and this c will become a velocity for, like, if you're driving down the road at 70 miles an hour, then it's not the speed of light, it's 70 miles an hour, which you can convert to meters per second, etc. And so we have energy equals energy, so we can have mc squared is equal to hc over lambda.
Okay.
Yeah.
So
So that's-
just since momentum was mass times velocity.
Okay.
I was confused at that point because I was like, wait, how does the speed of light just go?
Yeah.
to regular
Yeah, so
velocity?
that's the only trick to this problem is that c becomes v.
Okay. So
Yeah, and so then the squares cancel, and then this c becomes v for typical momentum. So this is p is equal to mv equals h over lambda. And that's the de Broglie wavelength relationship. And so, but it's, so for finite, no, not finite, but for velocities less than the speed of light, you can calculate the wavelength of me driving down the road at 70 miles an hour.
one of the reasons why I was confused is because it says velocity cannot be seen.
It says cannot be.
Yeah.
Well, I guess I can't reach C, but yeah, maybe I wrote that in a confusing manner. So sorry. Yeah. So that's and so then my wavelength, if you do that, it's like 10 to the minus 36 meters or something. So it's immeasurably small. So even going as fast as I'm comfortable going, you can't see my wavelength. I couldn't be diffracted, so it'd be kind of weird if you could be. You're going along and all of a sudden you go off in different angles. You're looking at, have you ever driven by like the Arlington Cemetery and you have all those diffraction angles or whatever? Maybe you do that and all of a sudden you go off in some pattern. Okay, never mind. It makes a lot of sense up here. Next question. Yes.
I had trouble with the one that talked about how many photons are emitted from the light bulbs if they're emitting 4 watts of light at daylight maximum.
Okay, yeah. Did you calculate the wavelength of that daylight using Wien's law?
Yes.
Okay, then if you have the wavelength, could you get energy? So the energy that wavelength represents. So go ahead and tell me what your wavelength was.
For daylight, the wavelength was 5.8 times 10 to the negative 5.
Meters?
Yes.
Okay. All right, so then, if we wanted to convert that to something to compare it to the visible region, because that was one of the questions, okay? Visible region is in nanometers. Okay, so we want to compare this to nanometers. Y'all comfortable with that? You can just do the meters here and nano there. We want to get nanometers. We want to get out of meters. Nano is 10 to the minus 9. Okay. And so then we have 10 to the minus 5 over 10 to the minus 9. Okay. So 5 minus a 5 minus a negative 9 is equal to plus 4, right? Okay, so we have 5.8 times 10 to the 4 nanometers. So it's longer than 800. So that maximum is in the infrared. Okay, but is the daylight wavelength shorter than the warm one? than the warm light bulb. Yes?
I think a lot of people are getting 10 to the negative 7.
Did I screw that up? Oh, 10 to the negative 7, okay. Okay. 10 to the negative 7, okay. 7. 2. 2. And then 580. Okay. So that's in the visible region. We're getting a lot of visible light out of that bulb. It's the daylight bulb, you know. Then you look at compare that to the warm. It should be a shorter wavelength because it's a hotter temperature. Okay, that's great. So we have this wavelength, 580 nanometers, and we want to convert that to energy using E equals hc over lambda. Okay. So once you find energy, what is that energy? Let's go ahead and make it joules. Okay. So we have energy in joules. And so that's very tiny energy. That's for one photon of light that's coming out. So this is the energy. Did anybody calculate what that was? So we can just write it down. It'll save us some time. A little louder, please.
I got 3.97 times 10 to the negative 29.
Yeah. Should be a small number. Okay. Think about a mole of those photons. You're going to have 10 to the 23rd of those. Okay. So this is how many joules one photon is, and this light is giving off how many watts in light? 4 watts. So 4 watts is 4 joules per second. Okay, and this is joules of light. And that light is for every, let me go ahead and write this out. One photon is 3.9 times 10 to the negative 29 joules. Right, because that was the energy for one of those photons at 580 nanometers. And so this will tell us how many photons of that light would be needed to make up 4 watts. And it's an absolutely enormous number. And it should be, because photons don't carry individually a lot of energy. So they're just blasting out of that light bulb, bouncing all over the room. That's why they go everywhere. There's quadrillions of them. Okay. And they go into every nook and cranny. You think, well, how could it possibly get to the underside of that desk? It's probability. You're spraying photons out of those light bulbs, and they go everywhere. If you only had one, it probably wouldn't go onto the desk. Okay? But if you throw out quadrillion after quadrillion, some of them are going to go onto the desk. Some of them are going to leak through the corner of that drawer and get inside the drawer. And so if you're inside the drawer, it's not going to be pitch black if the lights are on. Because 1 out of 10 to the 20th chance a photon's going to get in there. And we have a lot of those. Okay. So let's just kind of give you an idea of the scale of things, of how many photons are flying around. And so that helps us with spectroscopy. Now lasers are important because you take all those photons of 4 watts and put them in a single line. And you can beat the snot out of a molecule. Or you can burn your way through wood or whatever. So that's how laser etching and laser machining works. You're just sending all of those billions and billions and billions of photons in one direction, and you're just tearing stuff up. So I think that's pretty much time. If you have any further questions, just come up after class.